Welcome back. Stock prices can never go negative, but if you modeled them with a plain normal distribution, nothing in that model would stop it from predicting a negative price. That contradiction is the entire reason this video exists. The log-normal distribution and why it's the right tool for asset prices when returns are continuously compounded. By the end, you will be able to do three things. Explain the relationship between the normal and log-normal distributions. Explain why log-normal fits asset prices while normal fits returns. And calculate and annualize volatility from a series of continuously compounded returns. This matters because the log-normal distribution sits underneath option pricing models like Black-Scholes-Merton. Continuously compounded returns are the standard way volatility gets measured and quoted across the industry. If you've ever seen an annualized volatility number, this video is where it actually comes from. Here's the idea to hold on to. A variable is log normal if its natural log is normal. Say it as, the log is normal. That one sentence is the entire relationship in both directions. So a random variable y is log normal if ln of y is normally distributed. And the reverse works too. If ln of y is normal, then y is log normal. Why does this matter for prices specifically? A log normal distribution has two properties a normal distribution doesn't. It's bounded below by 0, so it can never predict a negative price. And it's skewed to the right with a long tail stretching upward. That matches how prices actually behave, since a price can rise without limit but can only fall to 0. Here's the actual mechanism behind that lower bound. The natural log of 0 doesn't exist, it runs off to negative infinity. So no matter how bad a continuously compounded return gets, the price it produces can shrink towards 0. The math never lets it cross to the other side. The mean and variance of a log-normal variable have their own formulas, built from mu and sigma squared, the mean and variance of the underlying normal distribution. The mean of the log-normal variable is e raised to mu plus 1/2 sigma squared. That's larger than you'd guess from mu alone, because more variance pushes the average upward, not sideways. The distribution can only spread up, never down past 0. The variance has an uglier expression still. This is exactly the kind of formula your sheet should carry, so your memory doesn't have to. So, here's the division of labor. Continuously compounded returns are well approximated by a normal distribution. Once you exponentiate those returns to get a future price, that price becomes log normal. Normal models the return. Log normal models the price. Mixing those up is trap number 1, and it's a common one. There's a bonus reason normal fits returns so well. Even if daily returns individually aren't perfectly normal, adding many of them together pulls the sum toward a normal shape anyway. That's a preview of something called the central limit theorem, which gets its own video shortly. Continuously compounded return has a specific formula. It's the natural log of the ending price divided by the beginning price. Why does the sum even make sense here? Because continuously compounded returns are just log price ratios, stacked end to end, today over yesterday, yesterday over the day before, and logs of ratios add. So the return from day 1 to day 10 is nothing more than 10 daily returns, laid end to end. All of this rests on one assumption worth naming, that one period returns are independently and identically distributed, or IID. Independent means one period's return tells you nothing about the next. You can't predict tomorrow's return from today's. Identically distributed means the mean and standard deviation don't change from period to period, a property called stationarity. Break either half of that assumption, and you can't just add periods together the simple way we're about to. Multi-period returns add up. The continuously compounded return over several periods is just the sum of the one period continuously compounded returns. And because of that, variance scales with time too, but not the same way standard deviation does. Variance over t periods is t times the one period variance. Standard deviation over t periods is the one period standard deviation times the square root of t. That square root is trap number 2. Multiply variance straight through by the number of periods. But standard deviation only scales by the square root of that number. Use the wrong one, and your annualized volatility will be off by an entire square root. Let's look at an example. Say Novatech shares traded like this over 5 days. After an earnings surprise moved the stock around. Monday, $84. Tuesday, $88. Wednesday, $85. Thursday, $90. Friday, $93. First, convert each day's move into a continuously compounded return, the natural log of today's price over yesterday's. Tuesday over Monday gives about 4.65%. Wednesday over Tuesday gives about negative 3.47%. Thursday over Wednesday gives about 5.72%. Friday over Thursday gives about 3.28%. Average those 4 daily returns and you get about 2.55% per day. Now find how far each day strays from that average. Square those deviations. Average them using n-1 in the denominator and take the square root. That gives a daily standard deviation of about 4.13%. To annualize, multiply by the square root of the number of trading days in a year by convention, 250. 4.13% times the square root of 250 is about 65%. For context, a typical diversified stock index runs somewhere around 15 to 20% annualized volatility. Novatech's week was more than triple that a genuinely turbulent stretch. That answers our first question. Volatility, annualized, is about 65%. Once you have that annualized number, what's it actually for? Options traders use it to price contracts. Risk managers use it to size positions and set limits. And it's the number everyone means when they mention implied or historical volatility in a research note. Here's a second question worth asking of the same data. Could you use that 2.55% daily average to estimate an annual expected return? The same way we annualize volatility. Multiply it out. 2.55% times 250 is about 638%. That number should stop you cold. Which brings us to question 3. Why isn't that a sensible estimate? 4 data points is not a sample. It's barely a coin flip, and the noise in 4 numbers completely swamps any real signal about expected return. Volatility can be estimated roughly from a short window like this because it's built from square deviations that stay reasonably stable. Expected return cannot. It needs far more history before the signal rises above the noise. One last question. Given that Novatech's daily returns are approximately normal, what distribution do the resulting share prices follow? Lognormal, bounded below by 0, skewed to the right. Exactly where we started this video. Memorize the continuously compounded return formula and the 2 annualizing rules, square root for standard deviation, straight multiplication for variance. But don't memorize the mean and variance formulas for a log normal variable itself. They're on your formula sheet. Look them up when a question actually needs them. Now, pause the video and try one. A stock closes at $50 on Monday, $53 on Tuesday, and $51 on Wednesday. Calculate the 2 daily continuously compounded returns and the standard deviation of those 2 returns. Tuesday over Monday, the natural log of 53 over 50 is about 5.83%. Wednesday over Tuesday, the natural log of 51 over 53 is about negative 3.85%. The average is about 0.99%. Each return deviates from that average by about 4.84 percentage points. They go in opposite directions, so squaring, averaging with n-1, and taking the square root gives a standard deviation of about 6.84%. So let's pull this together. A variable is log normal. If its natural log is normal, the log is normal. Continuously compounded returns are close to normal, which is exactly why the prices built from them are log normal, bounded below by 0 and skewed to the right. The continuously compounded return is the log of the price ratio. Variance scales by time, standard deviation scales by the square root of time, and volatility is estimable from a short window of data. Expected return is not. Next up in quantitative methods, how you actually get from a small sample to a trustworthy conclusion about an entire population. We start with the different ways you can build that sample in the first place. Thanks for watching, and see you in the next video.